can jump in.
Thanks, Jack, and thanks to all the organizers. Let me share my screen. There you go. So thanks to all the organizers. It's this coast to coast series is amazing. Like especially during the last 2 years. Like I haven't been south of Brisbane for like over 2 years now. So it's good feeling connected beyond Queensland. So that's great. Um, I would also like to acknowledge the traditional custodians of the land I am right now. So the Kabi Kabi people recognize their continuing connection to land, sea, sky, and community, and I pay respect to elders past, present, and emerging. So I'll try to be brief, but I need to start at the beginning. So this is basically where it started, probably over 20 years ago. And as a high school kid, I was really bad at drawing, really bad. Like I cannot draw a map, but I love maps. Like, and then one day I kind of like got told that satellites could take pictures of the planet. So that got me pretty excited. And then I decided to do geography as an undergrad, which was really uncommon. Back in Peru, where I was born and I did my undergrad, geography is not a scientific discipline which has progressed too much, unfortunately. But still, like just kind of like I knew I could use satellite images somehow. And of course, the other thing was like at one stage through my undergrad, I saw this photo of Andy Schwartz. And this is not a photo I saw. I saw some photo of him measuring some waves, probably at Narrabeen. And when I saw that, I asked my professor, I was like, is that something you do as a scientist? And he was like, yeah, of course. And he's pretty well known. So then I knew exactly what I wanted to do. I just kind of like was like, okay, if you can, be on like budgie smugglers and measuring beaches and waves, then that's exactly what I want to do. And it's funny because that's what I did. That's what I do. So 20 years forward, and I'm there. I couldn't pull the budgie smugglers photo, but still, I'm there measuring stuff using satellite imagery to try and understand coastal systems. So it's been a really interesting journey. Um, so I've kind of like had always a fascination with terrain, and very quickly I realized that elevation data, even though we live on an edge of like huge amounts of data, it wasn't that really available. Like good elevation data, in not like at the quality you need to assess things like coastal flooding and erosion. It's not necessarily something that has been widely available. So a lot of my research early on was trying to come up and trying to actually create this data. Here's an example of a few years back, Solomon Islands. Of course, Solomon Islands is very data poor, especially when it comes to elevation. And took me a few days to walk around this coastal village, complemented that with some SRTM and came up with a nice digital elevation model that we showed to the local village. And, we're running a few scenarios of what might happen as sea level rises and or tsunamis or whatever. So that was quite an experience. We even went ahead and actually built a hard copy or an actual 3D model of the region using cardboard, which was very interesting experience as well. And also we found that the people, even though they've never moved that much, they have this amazing spatial reasoning and they know exactly where things are. And that was just a great experience. But of course, again, going back to the data poorness, I guess, and especially when it comes to elevation, that was always a challenge. So then one day, someone sent me this paper. So this was published back in 2000, when was it? 2008. So I probably read it 2010. And these guys basically reconstructed the 3D structure of different sites around the world, sourcing photos from the internet. And when I read this paper, that kind of like changed my whole view, because I then understood that I could actually elaborate and create this data just using imagery. So this was one of these turning points in my career where I kind of like just went like, this is what I want to do from now on. So it was very, very a very kind of like disruptive event, I guess. And of course, I went into structure for motion, which is just basically kind of like using photogrammetric principles that have been used over 100 years now. But the real difference with structure for motion is that it actually leverages computer vision to make it easier to process and to generate this data. So Allman was the first one that I know of that proposed structure for motion back in the 1979, but he was way ahead of his time because the computer power you require to process images, it wasn't necessarily available to most people. So it took probably 2 extra decades to technology to catch up with this. But once it did, it revolutionized many fields. So archaeology were probably the first ones using it extensively, but geomorphologists came to the party very quickly, including myself. So it's very straightforward, really, using structure for motion, at least on the surface, and it consists on reconstructing the 3-dimensional kind of like structure of an object based on changing the position of images. So based on that overlap, and it's basically replicating what our eyes and brains do with overlapping eyes and having that sense of depth. So as long as you have enough overlap, and actually the more overlap the better, you can reconstruct quite precisely the structure of different objects. So what I'm going to do next is just give you a few examples of where I have been applying structure for motion. So underwater and above water. So the first application I found for structure for motion was to characterize structural complexity of coral reefs. And that's because at the time I was working on coral reefs, but also as a surfer, I was always impressed of how waves didn't kill me when I didn't make a drop, fell on the reef, and this huge thing just broke in front of me, and suddenly all this energy is not there. And so that kind of like has been on my mind forever. And once I kind of like connected the dots, and I was like, okay, I would like to characterize this complexity and then relate that to wave dissipation. Like this whole world open to me. So that was quite amazing. And of course, the first thing I realized was that ecologists have been characterizing the structural complexity of reefs for a long time, but the ways they did it were not kind of like the most what's the word, maybe cost effective. So chain and tape, that was and sometimes it still is one of the main or traditional ways of characterizing complexity, and literally it consists of laying out a tape and then just measuring that surface length and then dividing that by the planar length. So quite easy, but very time consuming. So here I am with structure from motion. I'm like all over it. So I just went out snorkeling and I was like, okay, I'll take a few cameras to increase that overlap. And I just swim around kind of like all of the coral reefs around the whole world. And I will just map out the roughness and structural complexity of every reef in the world because, that's what I wanted to do. Quickly, I realized that wasn't going to be the case. So for the first publication we had on this topic, I honestly was planning on mapping kind of like at least half of this reef flat. This is Heron Island, kind of like one of the southern reefs of the Great Barrier Reef. And we ended up mapping like this, the one transect, which was 100 meters, and that was a huge undertaking. So I guess the first lesson I learned was that the ocean is a huge place. So that's me swimming as fast as I can against a current. I have 3 GoPros with me, and this is my control point here. Really hard to lay out control on a reef flat. And then you can see the mountains back there. That's Dan Harris. trying to keep an eye on me. But yeah, so that, I guess that's the first lesson I learned, is like the ocean is huge. You cannot map at that kind of like scale, huge spatial extents, even though I knew that, but I kind of like didn't want to believe it. So there's always going to be a compromise between that, detail and that extent, even with new technologies. And this is not even considering the processing, which again took me probably a year to do back then with the computers I had access. So, but with time, we've starting to get better. So that's just one of a site up north of the Great Barrier Reef. And I mean, I'm still amazed of the detail you can get out of, this is just simple GoPros. So if you're using digital SLRs, of course, you get way more detail, but I'm guessing that, this detail, that's probably more than we need at this stage. But yeah, it's quite amazing. And of course, once you have this data, you can just compute rugosity, which is a pretty straightforward metric, which has been done, and it's still being done quite a lot. But of course, it's not necessarily the best metric. And on some recent work, we've been working with Dan Harris and colleagues. We're trying to go beyond rugosity. So looking at that multi-scale approach to roughness, because as you can see on this graph, like we've plotted here scale and roughness, and it changes significantly. Like as you change scale, then you'll have different expressions of roughness. So how to package this and how to kind of like come up with a simple metric we can use that incorporates that multi-scale approach, which is so important. So again, this is just, I mean, I guess I should have titled my talk New Tools for All Problems, because the problem of scale has been there forever. So, but I guess with these new tools and new data, we are able to tackle these older questions on different ways. So after a while, I kind of like, or I still do the underwater stuff, but of course, I was very curious to see how structure for motion would provide me on land. So then one day, drones became accessible. So one day, drones, you could buy a drone out of shops as easy as that, and quite cheaply as well. So up until then, I was actually experimenting with students just walking around, and I was using them as drones. So this is one of my students just carrying like a camera on a painting pole and just going up and down the beach to produce the model. So of course, once I got access to drones, that kind of like changed my whole approach to data collection, because now I could cover a larger extent at keeping that detail, and of course also increasing that temporal scale or that frequency of data collection. So this is Burgess Creek up in Noosa, where I live. So it's a coastal creek, really small catchment. It just goes like, it's just this area here. So literally it's a tiny catchment, and it's actually comes out of a wetland, and there's a sewage plant. So the discharge is actually controlled by Unity Water. So it's kind of like I guess a man-made or a man-modified coastal creek. But it's very interesting because it's probably the closest one to our main road up in Noosa. So this is a David Low Way here. And the coastal creek is, of course, highly dynamic. Sometimes it gets too close for comfort. So back in 2020, late 2020, the local council was actually quite nervous about the creek, because the creek was way on the dunes, too close for comfort. So what they did was they just brought one of these front pushers, like a front loader, and they just pushed through. So this creek could just go straight. Of course, that was ignoring my advice, because I told them that wasn't going to be a solution. And 2 weeks later, the creek was back to its original position. But anyway, that kind of like triggered me to start monitoring this creek. Given that I live very close to this area, I can do this literally every week if I want to, or every big event. So it's been going on for over a year now, and I still do it every now and then. So the results are quite great because it goes beyond that monitoring using imagery, which is quite useful. And we all know the advantages of frequently monitoring these type of dynamic systems. Because I mean, like council would rely on very sparse type of data, and they will go like probably once a year or twice a year, and they will just look at it. And if they do so, they could wrongly conclude that this creek is not moving that much, right? So this is over a year apart, and the position is like, it probably moved maybe 100 meters or less southwards. But that is not true, because the creek is actually very dynamic. So you can see here, this is 2021, so April 2021, and there's been almost 275 meters change south. So it's quite dynamic, and having that imagery derived from the SFM using the drone images allows us to kind of like track and monitor that highly dynamic system. So I had a student working on it, so she actually used some historical imagery, and we're trying to kind of like work towards a vulnerability assessment, and we're using the distance from the highway. So this black line here is a highway, and we're just using a threshold. So if it got too close to comfort, then it's a red alert for council, and we did this over time, and it's really interesting that these emergent patterns through time and space, and see some of these hotspots in both space and time. So what we're trying to do now with the drone derived data is just expand that. So for example, here we can see this is just a composite image, I guess, of all the wet pixels. So this is a percentage of wet pixels, and you can see that most of the time water is here, so the creek is here, but every now and then it's just moving around. So what we're trying to build on now is incorporating this type of I guess, dynamism onto vulnerability assessments. But this is just one of the products we get out of Structure for Motion. So Structure for Motion actually gets us the full 3D plus the imagery. So this is just using the imagery, but this creek, again, it has this discharge, which is managed artificially. But of course, there's a lot of influence from the coast, and the hydrodynamics here determine sometimes the behavior of the creek. So for that, we actually need elevation, and that's where these SFM-derived products become so handy. So we can see here 2 examples. So this is the 2020 image, and then this is the 2022, and this is just a difference. So this is just a change detection between the 2 dates, and we can see that there's a lot of movement going on. So up to 2 to 3 meters gain on this area. There's erosion on this part of the dune. There's some accretion as well to the south. So, like we start seeing things here that might inform management way better. And of course, the quality of the data we get from the drones is outstanding. We're getting orthomosaics at 3 centimeter resolution, and our elevation models are 5 centimeter resolution, and all of them are very precise. So with RMSEs of less than 5 centimeters most of the time. So this is very precise data, very cost effective, and we can do this frequently. And the frequency is very important. So if we zoom in onto like the one event, so this is October. October on the Sunshine Coast is the worst time of the year. It's flat, it's windy, it's horrible. Well, it's very nice, but not from a waves perspective. So this is when I kind of like I'm most bored on the year, and this is probably where I get more of this. I go out and survey more this creek. But anyway, this specific event was very interesting because as the beach built up, the creek kind of like was accumulating and was forming this mini lagoon type of thing. And then over this period, over that week, it was super calm, and the beach worm increased even more. So we can see here, here, the comparison of the beach profiles, and that's the 6th of October, and then that's a week later, the orange one, and you can see that beach berm kind of like increased 20 or 30 centimeters, but that was enough to kind of like, I guess the creek just kind of like got pounded and then just burst, or just got like, like just found a little channel there and made its way. So again, the importance of monitoring elevation through time as well, and at that frequency, is imperative here to understand the dynamics of the creek. So again, building up from this very simple approach to assessing the vulnerability of the road in this case, maybe we should be considering incorporating things like elevation range. So this, I guess this is similar to looking at the beach envelope or something like that, but on the third dimension. So again, it's showing the importance of looking at things on 4 dimensions. So not just kind of like our traditional, imagery survey or even our beach profiles, but extending that to the full 4 dimensions. So if you've used drones in the past, you can probably identify with one of my students here, as you safely land the drone, there's no better feeling. Just getting back your data, no one crashed, and you can see here, Ian is just going through that moment there. I love that the feast celebration there. But if you've used drones long enough, you should also be aware of all the challenges that imply using drones. So there's here in Australia, we have some regulations around flying drones. They're quite relaxed, to be honest, but still things like you have a top, so you cannot fly above 120 meters. You have to have line of sight. So this is for like your base level. So anyone could do it, as long as you're flying drones that are lighter than 2 kilos, then anyone can fly. But you have to stick to these rules. And for coastal type of work, probably the most limiting one is this one, where you cannot fly on top of people. And fortunately or unfortunately, I don't know, beaches up here are very crowded. So that means that most of the time it's really hard to fly a drone and avoid people. So the other regulations include flying away from airports, and we do have an airport close by, so that's an issue. And of course, you also need local laws, and if you're flying over a national park or private land, you also need a permit for that. So overall, it is quite challenging implementing monitoring programs using drones, and I'm aware of the Victoria Coastal Monitoring Program, and I can just imagine the challenges they've gone through, and I really admire what they've done down there. But unfortunately, even though I guess it would be ideal to distribute this work using drones along the coast, I've been finding it quite challenging. So this is where my third example comes in, and this is a very convoluted title, but basically it's a citizen science beach monitoring program, and it uses this real-time kinematic GNSS that assists with ground-based SFM. So it's called Coast 4D, and I acknowledge the support from Queensland government through the Engaging Science grants here to make this possible. It's very new, so it's very recent. It only started early this year. And basically, it's just an extension, a receiver that you attach to any smartphone. And when I say any, it's actually not any, but only Androids, unfortunately. But you attach that to your Android phone, and basically it overrides the internal GNSS that phones have. So instead of having photos that are geotagged and might have accuracies of 5 to 10 meters horizontally and vertically, is even worse, this little thing provides geotags photos to precisions less than 6 centimeters on horizontal and less than 10 centimeters vertical, and those are worst cases. And it does so by getting reception from satellites, and also corrections from, in this case, N-trip corrections. So we have a Queensland-wide service provider called SmartNet, and you get these corrections via phone. So as long as you have access to satellite, so you are outdoors and you have phone reception, then you are getting these corrections real time. And that allows us to geotag those photos very precisely. So then we can just ingest that into our SFM workflows. So this is just an example of how easy or how simple the equipment is. And literally all you have to do is take the photos, take overlapping photos. The results are quite amazing. You get orthomosaics of levels of detail of 1 mil, and your elevation models up to 2 mil, and your RMSEs on X, Ys, and Zs are below 5 centimeters. So in this case, was a nice day. Yeah, 5 centimeters vertical precision. So that's amazing. And the whole point of this project is putting this equipment on the hands of different volunteer communities. So I'm working with several communities along the Sunshine Coast, and each community has selected their sites of interest. So you can see here there's 10 sites spanning from Bribie Island on the south all the way to Noosa on the north. So people will go to the sites and revisit them through time. And it's amazing because in some cases, I have people walking the beach every day. So I'm getting data every day for some of these sites, which is, again, it's amazing. It's not all beautiful. There's many technical challenges, especially training the volunteers that requires a lot of time. But overall, I think it's a great exercise, especially from the engagement perspective and communicating what's happening and empowering the local groups to collect their own data and understand the local coastal systems. I think that's the biggest advantage of the project. In terms of data, I mean, like, I could potentially get some of these data way cheaper and easier using a drone, but it's the whole point of like kind of like incorporating citizen sciences on the journey, and also trying to distribute this work so we get more coverage over space and over time, so we can start addressing some of those questions that we've been trying to answer forever. So just to sum up, I mean, like, the technologies have definitely advanced, and we are now, we can now produce survey quality data with, you know, like our own phones, which is quite amazing. And we can go and buy drones from the shop for very relatively cheap prices and produce all of this data, which is great. But and this all comes into that, I guess, that same framework that we've been working on for a while now, which consists of mapping things and then monitoring and eventually modeling and predicting what might happen. So the problems remain, the questions remain, but yeah, we have these new tools to start addressing them from different perspectives, I guess. So yeah, thanks for listening, and I'm happy to answer any question.
Thanks, Javier. That was brilliant. Everyone have a think of questions, jump into the chat or put your hand up. I'll